Okay. Okay, this is there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Only 5 of you are there. Okay. Fine. I think we can start right away. So hope you're all ready. Shall we start?
Yes, sir.
Yeah. Okay. So we have been doing inductive effect, if you can remember, right? So we saw stabilities of what is that? Stabilities of carbocations and carbanions with the help of inductive effect, and we even saw how to decide acidic strengths. We know. Okay. So what is the criteria for acidic strengths? Like in the sense, how when will you say that the acid is having more acidic strength?
When the stability of conjugate base is more.
Correct. So when the stability when the conjugate base is stable, right? So then I say that the acid is a good acid. Okay. So fine. So then we went on to see if at all I have electron donating or electron withdrawing effects plus I or minus I. So with respect to that, I can say, okay, this acid is more stable, more acidic than this acid, or more than that acid. Like that, we'll be able to speak. Okay. Then we went on to see how to decide how to decide basic strengths, right? So basic strength. Now in organic chemistry, how do we decide which is a better base?
Check the availability of lone pairs.
Exactly, right? So more and more, so the only criteria, like at least in gaseous phase, right? So generally they will be asking you questions only in gaseous phase. So if they ask you in gaseous phase, right? So the only criteria for deciding the basic strengths would be the availability of lone pair. More and more the lone pair is available on that particular atom, say nitrogen, for example, right? So more and more will be the stability. So according to that, we decided, say tertiary amines will be more basic than secondary amines, because in tertiary I have 3 electron donating groups which are going to increase the availability of lone pair than secondary, and than in primary than ammonia, right? uh, but this might change a little bit, right? If I go for aqueous phase. Why? If I go for aqueous phase, there is a little change in the order which we saw in gaseous phase. Why is it that?
Because aqueous phase accepts or donates proton H plus.
mm, Aqueous donates. No, not exactly. In aqueous phase, what happens? I just need one word. I would say, okay, 2 words. What will happen if an amine is dissolved in water? What do you expect to happen? Yeah, so definitely you said that they're going to accept H plus. Okay, fine. So we're going to study about the conjugate acids of the base. So what will happen in the conjugate acids? How do you decide the stability now? Two words. Secondary bond.
Hydrogen bonding.
Yeah, correct. So it's all about going to be hydrogen bonding. So more and more is the number of hydrogens available on nitrogen. More and more will be the extent of hydrogen bonding. More and more will be the stability, right? So if I take only that into the picture, I will say that ammonia is a better base than primary, than secondary, than tertiary. But that is not the only criteria we should use. We should use the first criteria, that is your availability of lone pair, and in aqueous phase I have hydrogen bonding. So both of them put together, I gave you an order, right? So it will be secondary, primary, and tertiary, right? And in case of ethylamines, it will be tertiary. No. Secondary, tertiary, and primary. So something like that. I gave you an order, right? Okay. So these are all the things which we saw last class, right? So today, so that is about inductive effect, people, right? So inductive effect, we have seen almost in all cases where and all you have to apply. Okay. basically your carbocations, carbanion stability, acidic strengths, and basic strengths. These are the broad areas you'll be applying inductive effect. Okay, so we'll move on to the next concept, right? So the next concept, like basically we are seeing electron displacement effects, if you can remember, right? So in electron displacement effects, the first effect is what is my inductive effect, isn't it? Right. So the second effect that we're going to see today is this. Hyperconjugation. Okay, fine. So hyperconjugation is what, and obviously how with the help of this, how we are going to decide stabilities. Okay, so all that we'll see. Okay, now I already told you, right? So if at all there is a clash, right? If at all there is a clash between inductive effect and say hyperconjugation and resonance, right? So obviously, for example, say you find through inductive effect, you find that the particular cation is unstable, right? But through resonance effect, if you find that the cation is stable, right, you will always go with resonance. Okay, or hyper. So this is the order of preference, right? So inductive effect, hyperconjugation, resonance. So like whatever the results you drew, whatever the results you draw, right? So whatever you got with the help of resonance, if you have, that is the correct answer. Inductive effect, whatever it gives you, is not that important. Assuming that both of them are existing. If only inductive effect is existing, obviously we'll use only inductive effect, right? So if there is a clash, I'm telling this is the order of preference I will use, right? Hyperconjugation has more preference, and obviously resonance has still more preference than hyperconjugation. Okay, so anyways, we'll go for this. What is this hyperconjugation? Right, you should have definitely studied about this in your 11th class, but I'm sure that none of you would remember. Okay, let me ask, do you remember what is hyperconjugation?
No, sir.
Okay, definitely, right. Right, so yeah, so I'll tell you what is this, right? So basically, for hyperconjugation, so I would say this hyperconjugation, the another way of calling it is called sigma bond resonance. Right. So generally, right, whenever I go for resonance, right, I take only pi electrons. Okay, we'll see when I go for resonance, right? So you already know you have some knowledge about resonance. That's why I'm talking about it. So if I generally go for resonance, right, I will take only pi electrons. So when I say pi electrons, they are not only the electrons in a pi bond. No. So pi electrons can be in the form of a pi bond, right? Or they can be in the form of lone pairs, or they can be in the form of negative charges, right? So like when I say pi electrons, right, generally it's a misconception that only the electrons involving in a pi bond is what are called as pi electrons, but not necessarily, right? So I can have, sorry, it looks like an H, so pi. Okay, so the electrons involving in a pi bond, obviously, and even lone pairs, right? And obviously negative charges. And you should have seen enough examples for this, right? Say pi bond, benzene is a very good example. Only pi bonds are involving, right? Say lone pairs, I can say aniline, phenol. Obviously, oxygen has a lone pair, so that can involve in resonance, right? Or say negative charges, phenoxide ion, that is phenol. If I remove the H plus, the phenoxide ion, so there the negative charge will not involve in the resonance, right? So this is what is generally happens in a resonance. But here, if you look, right, I'm calling it as a sigma bond resonance. That means sigma bonds are actually going to get displaced, in the sense the electrons involving in a sigma bond are actually going to get displaced. Okay, now it's not like all sigma bonds are capable of doing this. Okay, so I would say only CH sigma bond. Okay, only CH sigma bond is capable of doing this. No other sigma bond is capable of undergoing hyperconjugation. Okay, fine. So we understood that there are going to be two electrons here, right, when in a sigma bond, right? Now these two electrons are going to get shifted to the, say, an empty orbital. That's what happens in resonance also, is it not? That lone pair, wherever you're shifting, right? So from the element, it is going to go to a carbon atom, maybe, right? It is going to go to a carbon atom which has a empty orbital. So obviously you need some space, right? See, the thing is, if at all electron is going to transfer, right? So if an electron is going to transfer, first of all, first of all, first and foremost thing is that I should have some electron to transfer. That is the condition, right? Second obvious condition would be, okay, the electron is getting transferred. So wherever the electron is getting transferred, there must be space in that particular atom for the electron to be accommodated, right? So obviously, when I say space, in chemistry, we mean that it is going to be an empty orbital, and it will be maximum empty p orbital. Okay, so that should be there, right? So what we have to understand is there are going to be two electrons in the sigma bond, right? Now these two electrons are going to involve in conjugation or involve in resonance with an empty p orbital of the next carbon atom. Okay, now if I give you an example, then you might understand better. Okay, so this is just an introduction. I will just give you an example. Okay, now let me take this case. I have CH3, CH3, CH2 plus. Okay, fine. Now let me write, say, this hydrogen as this, because I know I'm going to have hyperconjugation. Right? Okay, so first and foremost thing, so I should check whether I have a CH sigma bond. Yes, I have a CH sigma bond. No issues. Like, so many CH sigma bonds are there. Okay, now for hyperconjugation, I'll write the conditions. So first, a CH sigma bond is required, right? And the next condition is that the next carbon atom, that is, wherever the CH sigma bond is there, the next carbon atom to that, okay, should have an empty p orbital, right? It should have, because obviously we are going to donate the electron to the carbon atom. Obviously that carbon atom should have an empty orbital. Only then it is possible, right? Now you can understand, people, if I look at the hybridization of this carbocation, what is the hybridization, people, for carbocations? What is the hybridization of this carbon?
sp2.
Yeah, right. So it's sp2. Again, we know how to find the hybridization. It's number of atoms bonded to the central atom, 2 hydrogen atoms and 1 carbon atom. So 3. So 3 would be sp2 hybridized. So this carbon atom is going to be sp2 hybridized. Okay. Now I know what is happening here is basically, if you look at the carbon's electronic configuration, so carbon is basically going to have 1s2, 2s2, 2p2, right? So in 2s2 I have 2 electrons, in 2p2 I have 2 electrons. No issues, right? Then what I see, oh, it's a carbon plus. Okay, so if carbon is having a positive charge, it is not going to be 2p2, it is going to be 2p1 only, because 1 electron is lost, right? So this electron is not there. Okay, now this is the configuration for carbon plus. No issues, right? So now hybridization is going to happen. So for hybridization to happen, this electron will shift to the next empty orbital. So you will have a configuration like this is the ground state, this is the excited state of the carbon, right? So now you need 1 s orbital and 2 p orbitals. So 1 s orbital and 2 p orbitals, sp2 hybridization is gone, right? sp1 p2, done. Even after that, what you're seeing, there is 1 empty p orbital here. Okay, there is 1 empty p orbital there, right? So that is the requirement. So obviously, right? So if I have a CH sigma bond, and next to that, if I have an sp2 or sp hybridized carbon, okay, sp2, which will have 1 empty p orbital. If I have sp hybridized carbon, say in case of an alkyne, right? So at that time I'll have 2 empty p orbitals. But again, I just require 1 empty p orbital for hyperconjugation to happen. Okay, that'll be understood. Now, if I have an sp3 hybridized carbon, okay, when I have an sp3 hybridized carbon, no, hyperconjugation is not possible. Why? Because there are no empty p orbitals, because this p orbital will also be involved if I have sp3 hybridized carbon, right? So if I have a carbanion instead of a carbocation here, okay? So carbanion, you can easily, okay, fine. Now, I'll try to do this. What is the hybridization of this carbanion? Okay, this carbon atom, what is the hybridization?
sp3d.
sp3d. Does carbon have d orbital? Okay, we'll try to calculate what is the hybridization of a carbanion. Okay,
No, sir, it's
so let me.
sp3.
Okay, sp3 is the correct answer. Anyways, we'll check it, right? So first of all, I have to check for the atoms bonded to the central atom. In the central atom here is carbon. So you can see there are two hydrogen atoms and there is one carbon atom. So EP or say steric number would be 3 plus. And if you look at this, okay, now carbon has, okay, now look at this. Carbon has already 4 valence electrons, okay, excluding this negative charge. Carbon already has 4 valence electrons. Out of that, say 3 electrons. Out of the 4 electrons, 3 electrons are involving in bonding. How? One electron is involving in one hydrogen, second with second hydrogen, and the third electron is involving in a covalent bond with carbon. Okay, so 3 electrons are gone out of 4, right? So one more electron is left out. But what I have to see is that I have one more negative charge. That means instead of having 4 electrons in the valence shell, I'm going to have 5 electrons in the valence shell, and out of that, 3 are involving in bonding. I think I'm not confusing you, right? There are, okay, carbon 4 valence electrons, carbon negative will have 5 valence electrons. Okay, cool, right? In that, out of the 5 electrons, 3 electrons are involving in bonding with 2 hydrogen atom and 1 carbon atom, right? So in the valence shell, how many electrons are left out? 2 electrons are left out. Out of 5, 3 is gone, 2 is left out. So obviously that is going to act as a lone pair, right? So you can see, so, and I know steric number is going to be equal to number of atoms bonded to the central atom plus number of lone pairs in the central atom, right? So you can easily tell that steric number is 4. So definitely it's going to be sp3 hybridized. Okay, so if it's sp3 hybridized, this orbital which we saw empty last time, that also will involve in the hybridization. So definitely there are no empty orbitals. So for carbanions, there is no hyperconjugation, no, impossible. Okay, but for carbocations as well as free radicals, okay, what if this was a free radical? Then what would have happened? We'll see. Okay, right. So now, okay, so I'm going to check what will, okay, first of all, the only thing I need to check is what is the hybridization of a free radical? As simple as that, right? Now let me go for it. Now, what do you think? What will be the hybridization of the radical, free radical, the carbon? Yes, any answers? Any guesses?
Sir, is it still sp3?
Okay, fine. One answer is that. What about others?
SP2.
Anybody wants sp2? Okay, now we have 2 answers, sp2 and sp3. Can you can either unmute yourself or you can put it in the chat box. Now, how many of you feel it is going to be sp2 and how many of you feel it's sp3? Okay, now let me maybe okay, we will start this thing. So Harish says it's sp3. Sanjana says it's sp3. Okay, others? So until now we have got almost like 3 votes for sp3. Only 1 vote for sp2. Okay, Rahul again says sp3. So 4 votes. Okay, Aditi says it's sp2. Right. Okay, so we'll try to find it out. Okay, so again, going by the same method, finding the steric number is what I'm going to do. Okay, so number of atoms bonded to the central atom, 2 hydrogen atoms, 1 carbon atom, 3 is still staying. So this 3 is there, 3 atoms are bonded, right? Now I have to check for a lone pair. Okay, we'll check for a lone pair. So now, please understand, people, right? There are 4 electrons in the valence shell of carbon, right? Now, there is no positive charge, there is no negative charge, this is neutral, right? So 4 electrons means this here also I have only 4 electrons in the valence shell, right? Now, out of the 4 electrons, 3 electrons are involving in bonding with 2 hydrogen atoms and 1 carbon atom, right? So how many electrons are left out? Only 1 electron is left out. You cannot consider that as a lone pair. No. Okay, so please understand this, people. Lone pair means I should have 2 electrons. Okay, so carbon there is 1 electron which is not involving in bonding. I completely understand, but that you cannot regard as a lone pair because there is a single unpaired electron that is. So you cannot consider as a lone pair. So still it is going to be sp2 hybridized only. Okay, did I make sense? Right? So what you have to do is basically if you find a radical, a single unpaired electron, you should not consider it as a lone pair. Is that's what I'm telling, right? So in this case, I mean not in this case, any free radical for that matter will be sp2 hybridized, and all carbocations will be sp2 hybridized, and all carbanions will be sp3 hybridized. Okay, so you can actually conclude certain things here from whatever we saw. Hyperconjugation is not possible for carbanions. That's the first point. It is possible for carbocations and free radicals. And obviously, if I have any other type of sp2 and sp hybridized carbon, say for example, alkenes, right? So like we'll see examples, right? So what you need to understand is I should have an empty orbital, which is not possible when I have a carbanion. That's the only thing you need to understand. Okay, so we have understood all this. So that only 2 requirements, right? I should have a CH sigma bond, and next the alternate carbon, the next carbon should have an empty p orbital. If it is there, yes, hyperconjugation is possible. Very simple. Okay, now how am I going to see that? I told you that this bond is going to, okay, if it is a positive charge, whatever it is, positive charge or free radical, doesn't matter, right? So this CH sigma bond is going to break. Okay, I should not say break, but still that's how exactly you'll be able to understand. Okay, so I have these 2 electrons, right? Now these 2 electrons are going to go here, make a bond, right? And obviously this H plus is going to be gone. So H plus is going to come out. So now when I write the structure, I will be writing the structure like this. And what is left out? 1 H plus is somewhere here nearby. Oh wait, I think you're getting a glare. 1 second, I'll just close the window. Right? So yeah, so what I was telling is this hydrogen H plus is going to get lost, right? And there are 2 electrons here. These 2 electrons are going to make a bond. Obviously, this positive charge is gone, right? So, but what I have is H plus. Okay. Now, see, you can ask me, sir, how is it happening and all that? So you have an empty p orbital here. Okay. So basically, these electrons are going to get transferred to this orbital. That's how it's going to happen, right? So yeah, and basically a bond is formed, and this H plus is there. So this is one of the hyperconjugating structures. Okay, this structure, what we wrote for this, from this we wrote this, right? So this structure is what is called as my hyperconjugating structure, right? Fine. So obviously you bring in stability, is it not? How do you bring in stability? This was a charged species. I had a positive charge, right? Now the positive charge is not there. Like I made a bond, I made it stable. Just that I have H plus coming after. Not a big deal, right? So basically, more and more is the hyperconjugation, more and more is the stability, right? Stability and the amount of hyperconjugation or the number of hyperconjugating structures, right, are going to increase the stability. Understood? Right? This is one of the hyperconjugating structures. Now you remove this hydrogen, right? Sorry, right? So now you remove this hydrogen. I can either remove the other two hydrogens also. But again, the structure is going to be same. At a time, you can remove only one hydrogen because there is only one empty p orbital, right? So I have removed one hydrogen, so I can either remove these two, either of these two hydrogens also. So for this particular molecule, what I wrote here, CH3CH2 plus, right? If someone asks you how many hyperconjugating structures are possible, what will be your answer? Three. Yes, right? So obviously, how many ever alpha hydrogens you have, right? How many ever alpha hydrogens you have, that many hyperconjugating structures, right? So what do you mean by alpha hydrogen? I have a charged species, I have a radical or a carbon or a, whatever it is, right? The next carbon atom, this is called as my alpha carbon atom. Okay, so the hydrogen atoms in the alpha carbon atom are what are called as alpha hydrogen atoms. Okay, right. Now what I'm telling is the number of hyperconjugating structures hyperconjugating structures will be equal to the number of alpha hydrogens. Right? So, and I told you more and more are the hyperconjugating structures, more and more will be the stability. Right? So I can indirectly say that more and more is the number of alpha hydrogens, more and more will be the hyperconjugation, and more will be the stability. Okay. If you have how to put it, right? So if you are like in Tamil, if I have to say, if you are like organic chemistry, uri abdina, right? So like you can ask me, sir, okay, so this p orbital is here, okay, and I have this hydrogen atom here, right? Okay, they are parallel to each other, so this electron can be donated to this because they are in the same phase. Okay, fine, this hydrogen atom is okay, but what about other two hydrogen atoms? How am I saying that they also can involve in hydrogen bonding? Sorry, not hydrogen bonding, hyperconjugation. What will be your answer for that? Did you understand my question?
Yes, sir.
Wait. I'll repeat one more time. Maybe all of you would have understood. So what I'm asking is, I have a empty p orbital here, and I have a hydrogen atom here. They are in the same phase, like they are parallel to each other. So this electron can be easily donated to this, right? But I told you the other two hydrogen atoms can also involve, right? Now, how will you answer that? Because now they might not be parallel, right? The other two hydrogen atoms might be, say, one will be pointing away, the other would be, say, pointing or whatever it is, like the wedge and dash structures. Now, how will you account for it? These electrons, how can it involve here? What will be your answer?
So rotation of CC single bond takes place.
Yes. That's the answer. Now, maybe at this point of time, maybe you see this hydrogen atom here, right? But maybe after some time, due to the single bond rotations, so this hydrogen might have been here, or say this p orbital would have become parallel to this hydrogen, right? So how will you account for all the hydrogen atoms involved in hyperconjugation? You will be using obviously a concept of CC single bond rotations. Yes, that's the answer, right? So what and all we understood what is hyperconjugation, sigma bond resonance, CH sigma bond, and I should have a next star, a carbon atom, to have an empty p orbital. So obviously that electrons will be donated, right? So I told you more and more hyperconjugation, more and more stability, right? And how will you find the number? So what do you mean by extent of hyperconjugation? The extent of hyperconjugation will be higher with the number of alpha hydrogen atoms. More and more is the number of alpha hydrogens. More and more will be the stability. And that's what we said. Right. Now, I told you other than this, okay, obviously if it's a free radical also, the same thing will happen. For a carbanion, it won't happen because I told you it's sp3 hybridized. Okay, cool. Now, other than these charged species, right, I can even have this happening in case of alkenes. You'll be seeing hyperconjugation so many times happening in alkenes. Okay, so we'll see how that goes. Right? Say I have CH3, CH, double bond CH3. I have this molecule. Okay, so I will not like see. Okay, now first of all, these two carbon atoms are sp2 hybridized. Okay, now if at all I had another carbon atom here, maybe that also would have been able to involve in hyperconjugation. But this time I have only this carbon atom to the alpha, right? And the hydrogen atoms involved here can be involved in hyperconjugation. Okay, fine. Now, how will I write the hyperconjugating structures just like how you wrote last time, right? So let me write it like this: CH2, H. Now I have these two electrons. Now they are going to go there. So what is going to happen? I'm going to write CH2, CH, CH2, and H. Okay, so even an hope you understood, right? What I did, I had CH, not CH. Okay, now it's correct. Okay, so I had two hydrogen it's correct only. Sorry, I had three hydrogen atoms, right? Out of that, one is involved in hyperconjugation. Now the two electrons which are here will go here, make a bond. There's a double bond here, so and there's a H plus. So hyperconjugation is possible even in case of your alkenes. Okay, fine. Now, with the help of hyperconjugation, now with the help of inductive effect, we were not able to decide the stabilities of free radicals, isn't it? Because I told you inductive effect can be used, right? Only if I have charged species, especially for the intermediates, right? So you can do it only when I have charged species. But hyperconjugation, right, will help me find out what are the stabilities of free radicals also, right? Okay, now we'll go for some questions if you want. Right. So let me take a normal example, right? Say I have primary, secondary, and tertiary. Okay. So primary, secondary, and tertiary, if I take, say, for example, CH3, CH2 dot, CH3, CH dot, CH3, CH3, C dot, CH3, and CH. Okay. These are my primary, secondary, and tertiary free radicals. Okay. So from whatever knowledge you have learned now from hyperconjugation, tell me which is more stable, which is less stable. What will be the order of stability?
Sir, is it tertiary, secondary, and then primary?
Yeah, why?
Sir, because there are more number of alpha hydrogens present on the adjacent.
Yeah. So now you can see people, right? I told you the number of hyperconjugating structures, right? The extent of hyperconjugation will be higher with higher number of alpha hydrogens, right? So now this is the main carbon atom. So I have three alpha carbon atoms here, right? And all of them has hydrogen atom, right? So how many hyperconjugated structures are possible for this tertiary free radical? 9 hyperconjugated structures are possible because I have 9 alpha hydrogens, right? Now for this, how many hyperconjugated structures are possible? Now I have, this is the main carbon atom, this is my alpha carbon atom, this is also my alpha carbon atom, right? So now I have 6 alpha hydrogens, so 6 hyperconjugated structures are possible. Now this we saw last time itself. I have only 3 hyperconjugated structures possible. So definitely when I go for free radical stability, it is exactly similar to my carbocations. So tertiary will be more stable than secondary, and secondary is more stable than primary. Okay, this we need to know. See, hyperconjugation is the only way to decide the stability of free radicals. Resonance will not help you. Inductive effect will not help you. The only thing which can help you is hyperconjugation. Okay, fine. We'll take some more examples. Quickly, we'll do it. Right. So hope everybody understood what is this tertiary, secondary, primary, how we got it. Right. Okay. We'll take some more examples. Okay, let me give you the wedge and this structures. Okay, no problem. I'll give you this one. Okay, so I have these three radicals. Okay, if I mark it 1, 2, and 3, can you arrange them in the order of stability, people? Quickly.
Sir, is it 2, 1, and 3?
So many people gave answer. Harish gave. I think now it's Aditi. Okay, the answer.
No, sir. Sri Harini.
So yeah, sorry, Sriharini. Okay, so three of you gave answer and all of you are correct, right? So now I just have to check for the number of hyperconjugating structures. That means I have to just check for the number of alpha hydrogens. Okay, I just checked it. So now this is my alpha. This is my alpha. So 2 plus 1, just 3 hyperconjugating structures. Am I right? Yeah, I'm right. Here, this is my alpha hydrogen. So here I have this is sorry. This is my alpha carbon atom. This is my alpha carbon atom. So 3 hydrogens and 2 hydrogens make it 5. And here I have, so this is the alpha hydrogen. This is the alpha hydrogen. So 1 plus 1, only 2. So which is having the maximum number of hyperconjugating structures. 5 is the one which has, 5 in the sense, 5 numbers. So 2 is the one which is having maximum. Then comes 1, then comes 3. This is the answer. Hope everybody got it. Very simple. Hyperconjugation is the easiest concept, right? Okay, so yeah, that's about your hyperconjugation, right? Actually, there is one important thing. Okay, hope everybody got this. Okay, fine. Now, see, if I want to write the resonance structures, okay, say for example, if I want to write the resonance structure of phenol, it's very easy for me to write, right? How? Because I have, like, we will talk about resonance, don't worry, right? I'm just, since you know, I'm talking. So I have a lone pair, the lone pair will come here, this will break, and all these things will happen, right? Now, if I have CH3, okay, if I have toluene, this is what is called as toluene, right? Here, how will you explain the resonance, right? Now, before even going to that, now we know that my OH is an ortho-para directing group. That also hope we know. Ortho-para directing group means the incoming, if at all another group is going to come, that will be directed either to the ortho position or to the para position, because the resonance structures act accordingly. Okay, we'll again see that. But if you want to explain, now I know CH3 is also an ortho-para directing group. Okay, the incoming group will go to the ortho, this position or this position, right? Now, how will you explain that? How will you start the resonance structure is what I'm asking. Now, in this case, it's easy to start the resonance structure because I had a lone pair on oxygen and that is involving in resonance. That's okay, right? But how will you start here? Yes, hyperconjugation only, right? So it's very simple, right? Now I can see this carbon atom, what I have here is going to be sp2 hybridized, right? And obviously next to that, I have a CH sigma bond. Okay, right. Now, how will I start writing the resonance structure? Yeah, first I'll start with hyperconjugation. So this is how I start with it. So CH2H, I write it like this. Okay, so what will happen now? Now, if I remove this and write it as a H plus, now I had a bond here. So let's write it like this then. CH2H. Now this bond comes here and this bond, everything again happens like whatever happened here, right? Now this is just going to come out as this. Okay, so this is the in toluene. If you want to explain how it is going to be ortho-para directing, right? The only way you can explain with the help of hyperconjugation. Okay, so just now you saw I had CH3, CH2H, and I had this to be an sp2 hybridized carbon. So now this will come and eventually everything will happen. Again, it's going to be ortho-para directing. Okay, so yeah, these are all the various areas where you can use hyperconjugation. Is it understood? Right. Cool. Now we'll move on to the third and last concept of electron displacement effects. Right? We'll move on. Any questions from inductive or say from hyperconjugation? Any questions from you?
No, sir.
No, sir.
Okay, fine. Right. The next and most important one is resonance. So you already have a pretty okay idea about resonance. Fine. Right. So resonance, we know what is this. How do we define resonance? It is going to be basically delocalization of pi electrons. That's the simplest way to put it. Okay, it is the delocalization of pi electrons. Right? What do you mean by delocalization? Delocalization means movement of pi electrons is what is called as resonance. Okay, now we already said what can be pi electrons. So pi electrons can be in three forms, either in the form of lone pairs, or say negative charges, or say in the form of a pi bond, obviously. Right? So any of these three electrons involving in the electrons in pi bond, electron and negative charge, I mean, two electrons in negative charge, be very careful, right? And obviously, the lone pairs can involve in what is that, resonance. Okay, now before going to organic molecules, right? So let us take some inorganic molecules and check how resonance works. Okay, so let me take the example of ozone, O3. You are definitely known about it, right? So resonance structures exist in ozone also, right? Fine. So let me draw the ozone structure. I think this marker is done. I'll take another marker. So I had oxygen, one single bond. Okay, fine. I will give you 2 minutes time. Okay. I want you to draw, not even 2 minutes time. I'll give you 1 minute time. I want you to draw the Lewis dot structure of ozone. Go for it. Hope you know what is Lewis dot structure, right? So if that we have been studying from 9th class, right? So I'll give you a minute time. Quickly go draw the Lewis dot structure for ozone, O3. So if you have done it, maybe you can, not required. Yeah, Harish, that's correct. Well, and I know it's say if you're interested, you can like you can make a video on and show me what you have drawn if you're interested. But if you're not, it's okay. Like I don't know what situation you are in. That's why I didn't ask you. But if you're interested, you can show me. Okay, I think everybody would have drawn. Oh, you're using PC. No problem, no problem, no problem. No issues at all. No problem, Harish. Right. Okay. So yeah, what I was telling. So we'll try to draw. Yeah, Aditi, correct. Right. That is how it is going to be. O single bond O and O double bond O. But fine. Anyways, we'll try to do this. Okay. I have middle. I have an oxygen. Right. So this oxygen is going to have 6 valence electrons. Okay. So let me mark it. 1, 2, 3, 4, 5, 6. Okay, I'll write it maybe this side. 5, 6. Right. Now one more oxygen atom. Say that is also going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. right? And there is one more oxygen atom, and that is also going to have 6 valence electrons. Okay, right. Right. So let me do for first these two oxygen atoms, right? So both the oxygen atoms require 2 more electrons to satisfy its octet, right? So definitely this oxygen will take these 2 electrons, and this oxygen will take these 2 electrons. Done. So a double bond is formed. No issues. 4 electrons are shared, and 2 bonds are formed. Done. Right. Now this oxygen atom does not require any more electron because it's already octet satisfied. But for this, I require 2 more electrons. How will you account for it? You cannot donate electron to this because it's already octet satisfied, right? But still, you told me that there's going to be a single bond. Oh, double bond is accounted for. There's going to be a single bond between this oxygen and this oxygen. But how will you account for it? I'll give you 30 seconds time. Think about it. Lone pair. Okay. What I'm going to do is a lone pair, Harish. I think almost the time is over. 30 seconds. I don't know. No, I didn't count it. Any answers? Okay, let me give you a clue. It's a special type of covalent bond. Hope you heard the clue. I told it is a special type of a covalent bond. Ah, yes, Sanjana, correct. It's a coordinate covalent bond. That's the answer. Definitely. So what you see here is that there is going to be a lone pair on this oxygen atom, and this is going to get donated to the next oxygen atom. And this is like sharing only, right? So these electrons are involving in this also, but just that these 2 electrons are going to get shared to this oxygen atom, making a coordinate bond. So how exactly will you draw the Lewis dot structure? So remember, people, when I ask you to draw the Lewis dot structure, I'm not only asking the bonds. When you draw it, you have to include the number of lone pairs in each of the atoms. That's the say full complete Lewis dot structure. Okay, so if I want to write it now, this is how I write it. So there is going to be a coordinate bond. So whenever you want to represent a coordinate bond, it has to be represented like this. From which atom to which atom? So that direction, the arrow should point. Okay, and obviously I have a double bond. Oh, also let me check how many lone pairs are there. So these 2 lone pairs are gone. So there's only 1 lone pair on this oxygen, and I have 3 lone pairs on this oxygen and 2 lone pairs on this oxygen. So this is the perfect Lewis dot structure. Yeah, almost all of you got it, except that maybe you are not able to represent the lone pairs while you answer me. It's completely all right. So yeah, this is how it's going to be, right? So what I understand is, right? So I have a single bond and I have a double bond between the oxygens, right? So generally, what do I expect? I expect, right, a double bond to be stronger than a single bond. Obviously, right? A double bond is stronger than a single bond, right? So obviously, if I compare the bond lengths, what is the distance between the 2 oxygen atoms? Obviously, a stronger bond, the atoms will be very, very close to each other. A weaker bond, the atoms will be a little far away from each other, right? So obviously, I expect this bond length and this bond length to be different because it's a single bond and a double bond, right? But what I see in reality is that both these bond lengths are same. That I get it from my spectroscopic studies. Okay, don't worry about the term which I told you now. You will study if you're interested in chemistry. Maybe if you take BSc chemistry, maybe you'll be studying about it. Okay, so I'll be able to find the bond lengths There are so many ways to do it. But anyway, so what I found is this bond length and this bond length are same. Okay, so then scientists started thinking, how do we explain this, right? So then came the concept of resonance. Okay, so what they said is that, see this lone pair which I have here. Okay, and again, for resonance to happen, I should have pi electrons, and the next atom, wherever you're going to put the electron, should have an empty orbital. Obviously, this has an empty orbital because I know only two atoms are there. So it is going to be sp hybridized. Oh, lone pair is also there. So sp2 hybridized. Okay, right. So anyways, I have an empty orbital. That's what I need to understand. So what I'm going to do is I am going to put these electron here. Okay, fine. If I put the electron, now please understand people, right? So oxygen cannot have more than 3 bonds. Actually, it cannot have more than 2 bonds itself. But since it's a special case where coordinate bond is forming, it is forming 3 bonds. So definitely more than 3 bonds or oxygen is not possible, right? Now, if you make the bond here, make a bond here, oxygen is going to have 4 bonds, which is not possible. So what you have to do is that you are going to break this bond and put it to the next oxygen atom. Okay, now how will I write the resonance structure? Now this is what is happening. Now how do I represent it? Now please understand people, this oxygen atom has lost electrons. Correct? This oxygen atom has lost electron. So this oxygen atom is going to have a positive charge with 2 electrons. Okay, and still a double bond is going to exist. Say one of them is coordinate, but I'm not representing. So there is one more oxygen atom with one lone pair, and this bond became a single bond, right? And this oxygen atom has gained electrons. So there is going to be a negative charge, and there are going to be 1, 2, 3, 4, 5, 6 lone pairs. I mean, 3 lone pairs. Okay, and this is the resonance structure. Okay, what will be the next step? Next step would be, again, if you want to go back, again, these 2 electrons will come here, these 2 electrons will go there, again, you will get back the original structure. Okay, so what you understand from this is that the double bond which I have here, right, is getting oscillated between this oxygen atom and this oxygen atom. Okay, so that is why, okay, so if that is going to happen, so sometimes double bond can be here, sometimes double bond can be here, right? So now these 2 are the resonance structures. Okay, now if I want to represent the ozone molecules structure in only one structure, including resonance, okay, so including all the resonance structures put together, if I want to represent in one structure, right, these are what are called as resonance structures, and I'm going to have something called as resonance hybrid. Okay, so resonance hybrid is going to be the structure which will include all the structures in one structure. Right, now how am I going to represent it? We'll see. Okay, I'll write it here. So first you put the single bonds. Okay, first you put the single bonds. Now what you're going to do is that the double bond is oscillating between these 2 oxygen atoms, right? So you will represent it like this. Okay, what you're getting, there's a dotted line between the dotted curve, I would say, starting from here and ending here, right? Now this indicates that the pi bond is oscillating between this oxygen atom and this oxygen atom. Okay, right? So now if I check the bond length, I told you double bonds are stronger, single bonds are weaker. So now what I see here is that the bond length is little bigger than a double bond. Okay, obviously the double bond are stronger. Now you see that the double bond is oscillating between these 2, right? So if I take any 2 oxygen atom at a point, right, the bond length is little greater than the double bond, but lesser than a single bond, because it is neither a double bond nor a single bond. It's a hybrid, right? So I would say the bond order, you would have studied about bond order in your chemical bonding, molecular orbital theory. So the bond order for each of the 2 pairs of oxygen atom would be 1.5. 1 means 1 bond, 2 means a double bond, but 1.5 is in between that. Again, the bond length will also be such, right? It will be lesser than a double bond, sorry, single bond, but greater than a double bond. Okay, so this exactly is what is resonance, people, right? So movement of pi electron. Okay, now I can apply this to my organic molecules also, right? So obviously you will see more application of that in organic molecules only, right? Okay, fine. So we'll try it. Now, if I don't want to spend so much time on this resonance because you already know it. What we'll try to do is that we will take your benzene molecules, like the derivatives of benzene, all these things we'll try to take, and then maybe we'll try to see what happens there. Maybe I can try to explain the resonance structures there. Okay, right? We'll try to do that. Okay, now there are certain rules for writing resonance structures, right? The first rule is that you should not break or make any new bonds. You should not break any existing bonds. You should not make any new bonds. All the bonds, say for example, I have a CH3 here. That CH3 should stay throughout the entire structure. You should not alter the atoms basically. Wherever it was, the atom should be there only. Only the pi bonds can move. Okay. And next thing, if you are going to shift a pi bond, if you're going to put it to the whatever, you have to put it only to the next atom. You should not put it 2 carbon atoms away, 3 carbon atoms away. You should put on only 1 carbon atom, like next carbon atom basically. That's what you need to do, right? Okay. So we'll take benzene, right? We will try to explain what are the resonance structures. Okay, fine. So we'll do it step by step. Right, now this is one of the structures for benzene. Okay, now what I do is that now I take any of the double bond. Okay, now I have this double bond, right? Now this double bond I am going to heterolytically, no, not required. Fine, let me put it that way. Okay, I am going to heterolytically cleave it. Okay, heterolytically means one of the carbon atom is going to have a positive charge, another carbon atom is going to have a negative charge. Okay, now let me put it like this. This goes to this carbon atom. I told you, you can shift it only to the next carbon atom. See, the pi bond will break. Pi bond will break and you cannot directly put it here. But that is what is going to happen. But I'm just showing how the bond will come here. Okay, so if this undergoes heterolytic cleavage, I can see that this carbon atom has lost electron, so there'll be a positive charge, and this carbon atom has gained electron, so there'll be a negative charge, and the other 2 bonds fix. Okay, now see, when I say this thing, there are going to be 2 electrons here. Both the electrons are lost, and that's why it's here, and there's a positive charge. Next, what can happen? Now this, again, this is a lone pair, or however negative charge, or whatever it is. Now this can come back here, make a bond. Now, if this forms a bond, obviously this carbon atom will have 5 bonds because there's already a hydrogen atom here. 1, 2, 3, 4, 5 it will become. So what are you going to do? For this to happen, obviously the next one has to go to this carbon atom, making it a negative charge, right? So now what will happen to the next structure, right? So I have this bond staying and the positive charge is still there. And now I made a new bond here, right? And what I have is the negative charge on this carbon atom. Yes. Okay. Next, what is the next step? Again, I have a 2 electrons, so this will come, make a bond, and obviously this bond has to break and make a negative charge. Right. So this will come here. I still have the positive charge left, and I have, okay, this bond is still staying. Okay, maybe that will make this right. So this bond is still staying. Now this has formed a bond here, right? And there is a negative charge here. No issues. Okay, right. Now again, I have 2 electrons. Now this is gonna go here, and that's it. The positive charge will be gone, and a new bond is formed because electrons are getting donated, isn't it? So the last structure will be like this. Now I had a bond here, I made a bond here, I made a bond. Right? So everybody understood what is happening? Okay, So like now, if at all you want to make it a shortcut, if you want to make it simple, this thing. So what you can do is, now I can reduce one step every case. Now what I can do is, now you make sure that you break the bond if I'm a negative charge, or you can directly say that I'll put the bond here, then this bond comes here, and this bond goes here. So hope you understand how that is happening, right? That is happening because this bond undergoes heterolytic cleavage, makes a lone pair or a negative charge, and that comes, and then the bond breaks, again a negative charge. This goes, again a negative charge, and then at last the positive charge is bond. Okay, so this is how you write the resonance matrix of benzene, right? Okay, fine. So I think now you would have got a good idea of how to write the resonance structures, isn't it? Right? Maybe I will take again benzene derivatives. We know that certain groups are going to be ortho-para-directing, certain groups are going to be meta-directing. So we'll try to prove how is it happening like that. Okay, maybe that again will give you a good picture of how to write the resonance structures, right? Okay, fine. Oops, were you copying the structures, people?
Yes,
Did I
sir.
rub it before you get copying? Before
Yes,
you
sir.
copy? Oh, I'm really sorry. Wait, I'll draw it again. No issue. It's not a big deal. So what happened? I had a bond, negative charge, this. Okay, next. This will come here, this will break. Oh, there's a positive charge, obviously. One bond, a negative charge, and a positive charge. Now again, I have two electrons. Now this will come here at last. 1, 1, 1. Yeah, that's it. These are the structures.
Done, sir.
Yeah, cool. Thank you. So now we'll take some derivatives of benzene. Maybe I'll take one ortho-para-directing group and one meta-directing group, and we'll see how they're actually meta-directing and ortho-para-directing. Okay, fine. Okay. How much time is left? We have 20 minutes. Okay. Fine. Now let me take the famous. Okay. Now, okay, I forgot to tell you one thing, right? So we saw so many resonance structures for benzene, isn't it? Right? Again, those are all the resonance structures, or resonance structures are also called as canonical structures, right? Resonance structures, all the resonance structures are also called as canonical structures. Okay, and okay, now we saw in case of your ozone, we saw two resonance structures, and there was a structure which was able to represent all the resonance structures in one, right? And we named it as a resonance hybrid, correct? So benzene also can have a resonance hybrid, right? Comprising of all the resonance structures. I can have a resonance hybrid for benzene, and resonance hybrid for benzene is this, right? So if at all you maybe you would have what's say thinking, why was there's a circle in the center of the benzene ring, right? So that circle actually represents the pi electron cloud is rotating, I mean moving inside the ring. Okay, so anyways, so this is the resonance hybrid of benzene. So now we'll take another OH, right? Now people, please understand, right? So the most common type of reactions benzene or benzene derivatives can undergo is electrophilic substitution. Electrophilic substitution. These are the most common type of reactions benzene and its derivatives undergo. Right. Now, from the name itself, you can actually listen what exactly is happening. Right. So you can see that electrophilic substitution. There is, what do you mean by electrophile? I told you nucleophile is negative charge. Electrophile, electron phile, electron loving species. So that means they are negatively charged loving species. So there must be a positive charge. Okay. So from the name electrophilic substitution, what I understand is one positive charge is replaced by another positive charge. Okay, one positive charge is replaced by another positive charge. So what exactly is going to happen? So generally, H plus will be replaced by an electrophile which is going to have a positive charge. Okay, H plus is going to get replaced by an electrophile. And the electrophile, like, it can be Br plus, it can be CH3CO plus, CH3 plus, it can be any electrophile for that matter. Okay, NO2 plus when I go for nitration. So anyways, we'll see the mechanisms later of how it's going to happen. But for now, what you have to understand is the majority of the reactions will be electrophilic substitutions. Okay, one hydrogen in any of these places, right, will be replaced by an electrophile. Okay, fine. So for the electrophile to attack, okay, for the electrophile to attack, there should be negative charges. Obviously, only then it will go on attack, right? So in the resonance structures of any of the molecule, in this case it's phenol or it can be nitrobenzene. So wherever you find negative charges, whichever positions you see negative charges, those are the most favorable positions for the electrophile to attack. Again, I repeat my statement, right? So in the resonance structures of phenol or whatever the molecule is, right, in whichever position you are able to form a negative charge, right, those are the positions which are favorable for the electrophile to attack. Hope you get my point, right? Now, I want you to do, I want you to draw the resonance structures of phenol. Go for it, right? So you already know where you have to start. You have to start with the lone pair on oxygen. Go for it. I'll give you a minute's time. Quickly, I want you to draw all the resonance structures. Go for it. You have a lone pair. Obviously, there are two lone pairs. So from there, you have to start it. Now, just like how I drew last time, every step should be explained, not like directly putting the bond from here to here. No, I want you to show the heterolytic cleavage, then make the bond. Okay, I think you should have done it by this time, right? Fine. So let me write the structures and you check whether you wrote it correct or not. Okay. Right. So the first step, as I told you, the lone pair will make a bond here. And obviously, if this makes a bond to this carbon atom will have five bonds, which is not possible. So definitely this has to undergo heterolytic cleavage to here. Right. So what will be the structure? The structure would be, now oxygen carbon had only single bond before, but since the lone pair is involving in resonance, you would have had double bond OH. And one more thing, oxygen atom is losing electrons, so you should give a positive charge to oxygen. These are all the small things you have to take care when you're writing the resonance structure. Okay, So first double bond is formed between carbon and oxygen, and you know that oxygen atom is losing its electron. So definitely I should give a positive charge to oxygen. Okay. Now what you see here is that these two electrons are going to go to this carbon atom. So electrons are getting gained by this carbon atom. So you have a negative charge here and 2 more bonds are there. No issues. I think the first answer you got. Why is it that phenol is going to be ortho directing? You can directly see that in ortho position, you formed a lone pair. Sorry, you formed a negative charge. So the most favorable place for the electrophile to attack would be that negative charge in the ortho position. Okay, now we'll continue. Okay, so now what is the next step? Now I have 2 electrons. Now these will come here, and obviously this has to break. So the next structure, again I have the double bond OH plus still staying. Now I had a bond here. Now this bond has broken. Again, why this bond works? Because carbon is going to have 5 bonds. That's why, right? So this, I have 2 electrons and this is still staying, right? Okay, next step, this bond will go here and this is going to go to the next carbon atom. So you will have a double bond OH plus and a negative charge here, obviously, because the bond is breaking heterolytically, and you made a bond here and there is a bond here. And what is the last step? Last step is going back to wherever we came from. I have 2 electrons. Now this is going to come, make a bond here. Obviously, this carbon atom cannot have, this carbon atom cannot have 5 bonds. So this will go back to your oxygen atom, right? So what is the final structure? Final structure would be a bond here, a bond here, and a bond here with an OH. Okay. Now, where and all do you see negative charges, people? You saw negative charge in the ortho position, and there is a negative charge in the para position. So you got your answer, right? So why is it that electron donating groups like phenol, NH2, OCH3, all these things, why they are ortho para directing? It's very much understood that from the resonance structures, because you form negative charges only at the ortho and para positions. Ortho position, para position. Right? So this is understood. Right? How many of you got all the structures correct from this?
Sir, I got confused at the last one.
No issues. Sanjana says she got it. Good, Sanjana, if you got it. Right? So yeah, very simple. Right? So there is, okay, Siddharth also got it. Sriharini also got it. Good. Right? So see, I got it in the sense along with the charges, like along with the bond breaking, along with the arrow marks, everything should have been perfect. If you have gotten all these things perfect, then very good, right? Along with the charges, the arrow marks, where you're going to form the bond, everything should be perfect. If you got it, very, very good, right? So yeah, so this is all the resonance structures, right? Now we'll take one example of an electron withdrawing group, that is basically going to be a meta-directing group, and we'll see what happens. Okay, fine. We'll try to do this. Okay, if someone is taking this down, I'll give you 30 seconds. Quickly take down. Okay, should be done by this time, hopefully. Okay, cool. Right. So we'll take nitrobenzene. That's the best example I can have, or even you can take say acetophenone. Anything is fine, but I'll take nitrobenzene. Guys, just give me a moment. I'll be back in a minute. Okay, yeah. So now we'll try to draw the resonance structures of nitrobenzene. Okay, so the bonds are here. Cool. Right. So now what is going to happen? Right. So they tell you that nitro group or like say OC, what is that? The C double bond O, all these things, right, are going to be electron withdrawing. Right. How they electron withdrawing, now you have to understand. Right. Now this nitrogen, it actually doesn't have a lone pair. Okay. Now how can I say it doesn't have a lone pair? Now you can see that there are going to be 5 valence electrons. Yeah, 5 valence electrons in nitrogen. Okay. Now 2 are already gone here, right? And what do you see? There is a bond. Okay, the one more electron is gone here. 3 electrons are gone. And what do you see after that? After that, you see a nitrogen 2 oxygen coordinate bond. So 2 electrons were there remaining, and those 2 electrons have gone as a coordinate bond to the oxygen. So done. There are no lone pairs. So that lone pair, if there's no lone pair, obviously that cannot be donated, right? So the only way I can start the resonance structure is by making sure that I break this bond heterolytically. Okay, so if I make this bond heterolytically, say this bond goes here. Okay, so if this bond goes here, right, I'll write okay. Now I have a negative charge on this carbon atom, positive charge on this carbon atom. Hope you're able to see the positive and negative charges, right? There's a bond here, there's a bond here. Okay, now next step what would it be? Obviously there are 2 electrons here, so these will go here, and obviously this bond has to break, right? So what is the next step? Okay, let me go a little down. I had nitrogen, oxygen minus. Now this bond has broken, definitely oxygen will have a negative charge, and this stays. And what I see is that I made a bond, so there is a C double bond N. The positive charge still stays on this carbon atom. And obviously the other 2 bonds. Yes. Right? Cool. Any questions? So the first step is breaking this bond heterolytically, making a negative charge and a positive charge. Right? Now this negative charge is going to make a bond with nitrogen, and obviously the nitrogen cannot have more than this many bonds, so that will break to make a negative charge on oxygen. Cool. Right. So what will be the next step? Obviously, now I have a positive charge. Okay. Again, I can make it into 2 steps. What will be the steps? I can bake this heterolytically, make a negative charge, and that negative charge goes attached to positive charge. I mean, make a bond, basically. That's what I'm trying to say, right? So maybe I can show it to you. Say this will go to this carbon atom, right? So it will be a heterolytic cleavage. So what do you think will happen? I have double bond NO minus O. Okay, now the bond has broken heterolytically. So there will be a positive charge, there will be a negative charge, there will be a positive charge. Okay, so now what is going to happen? Obviously, now this is going to go here, and these 2 are going to get neutralized. So what is the next step? O minus O. So there was a bond here. Actually, you should not show the negative charges. That's fine. I will show the negative charges. It's actually going to help me. Fine. So there was a bond here, and there was a positive charge here. Actually, I missed the other bonds. The other bond is basically this one. Okay. So now this bond still stays. Okay. Next step. So obviously the same thing what you did here. You break this one, this bond. Okay, you break this bond heterolytically, make a negative charge, positive charge. This will come, this will go. Exactly what you did from here. You broke this, made a negative charge, and that goes. Okay, so now what I'll do is I'll directly put the bond. I'll put the bond directly, has a bond here. Okay, but still this carbon atom has lost electrons, right? So next structure, P, double bond, NO minus, and O. So now this carbon atom would have had a positive charge, and a bond is formed here, and a bond is formed here, right? Okay, now what will be the last step? Tell me, from where should I start for the last step? Guys,
Go back to
I'm gonna go
start,
for-
sir.
sorry,
Go
sorry.
back to the start. Go back to the start.
Yeah, that's what I have to write the resonance structure for this, right? I have to start the resonance structure from somewhere, and I have to go back to the initial whatever I got. Where should I start? That's what I'm asking. The resonance structure, this particular resonance structure, where will I start it from?
So that O bond.
On the
is-
positive charge.
From the positive charge? No.
Sir, from the oxygen atom having a negative charge.
Yes, that's where I should start it, right? So how will I draw it? Now this bond will come here, make the bond, and obviously the carbon cannot, I mean this nitrogen cannot have more than this. So this bond would have come here. That's it. Okay, everybody understood, right? So this bond would have come here, made a bond. So again, if you want, you can do it again. Make a heterolytic cleavage, make a negative charge, and next step again you can make the bond. It's up to you, right? But now since that we have seen so many, I'm just putting directly. The last structure would be N double bond O minus. Now I have a bond here, right? Yeah. I have a bond here and a bond here. Right? Now, going back to the question, how is it that my NO2 group is going to be a meta-directing group? So what I have to look for? I have to look for where and all negative charges would have been formed. So you can directly see negative charge was formed in the meta position. Okay, now why don't you see it here? Because we skipped the step. Now, if you look at this bond, I want the first step can be like this, making a negative charge, and the negative charge attacks here. So anyways, you would have seen that a negative charge is formed here, a negative charge is formed here. Only in meta positions, right, negative charges are formed. So obviously, an electrophile which is incoming will prefer to go to the meta position and not ortho and para positions. Okay, so please understand this electron withdrawing group. See where I'm starting the resonance structure. I am putting the resonance structure starting from carbon, in this case, the benzene ring, right? But if it was an electron donating group, right? I should start from the element from where the lone pair is coming. That's where the resonance structure starts. Okay, so there it was ortho-para directing. In electron withdrawing groups, they're going to be meta-directing. Okay, that question is answered, right? How much time is left? Okay, almost 8:30. Okay, I'll stop here, right? So we are almost the end of the chapter. I have to teach you a little more resonance, where and all you'll be using it, and maybe we'll go for problem solving session. So I'll be requiring almost like 1.5 hours plus maybe 1 hour, something like that. I'll be completing this chapter, and next we can go for hydrocarbons. Okay, now these are all the basics. Now you'll go for the exact reactions, organic reactions, and you will apply whatever has been told to you till now. Whatever you have learned in this chapter, you will all be applying that in the next chapter. Not only that chapter, entire the organic, what are the chapters to come, all these things. Okay, so any questions? Okay, so I assume that there are no questions. Thank you, people. We'll meet again tomorrow. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.